let's read through these warm-up questions together. In essence, what is function notation? So in as many different ways as possible, how do we describe and talk about this thing called f of x equals x squared plus 5? Just what are some thoughts that come to mind? Just what would you say to somebody?
A potential solution for a graph.
That it what?
It's a potential solution for a graph.
A potential solution for a graph. You've got a lot packed in there.
Like in the sense of if anything is plugged into x, it gives you to a graph.
Right, very good. So as you plug numbers in for x, so like if I input some number here, then whatever number I input into this function, this whole thing is going to compute an answer, which will then become an output. And then that input and that output together, we call a coordinate on a graph. And then that's what this function is, really. This function is just a collection of infinitely many pairs of input, output, infinitely many of them. And if you take them all together and draw them, then what you have is a picture of a graph. But you know what that picture is really just infinitely many coordinates all stacked together in a row, which are all just pairs of input outputs that you plugged into that function. So yes, that's one great way to start. You said something else, Chelsea. You said something about a potential solution.
Yeah.
Where are the solutions? When we use the word solution, we're referring to one particular thing. Yeah, the solution is always the x-intercept. So ironically, does this function, because that really is the graph of this function, does this function have a solution? And it doesn't have an x-intercept. So you would think, well, no, there's no solution because there's no x-intercept. But remember, we learned that every polynomial has a solution. And in fact, how many solutions does this one have? At least two, exactly two. And so these two solutions, though there are no x-intercepts, what kind of solutions does it have? Imaginary. So this thing does have imaginary solutions. Now, if it did have an x-intercept, we learned to look at a function and say, hey, anytime it touches the x-axis, that's where f of x equals 0. So does that mean that this graph doesn't have any places where f of x equals 0? Technically, it still does have a place where f of x equals 0. It's just imaginary. So now if I take this function and I set it f of x equal to x squared plus 5 equal to 0, and then I move the 5 over and I get x squared equals negative 5, and then I square root both sides and I get x equals plus or minus root negative 5, which is really x equals plus or minus 5i. So there are, in fact, two solutions, positive 5i and negative 5i. And those are the two different numbers that will make f of x equal 0. It just happens to not be an x-intercept in a visual sense according to our eyeballs. But it's still a solution to the extent that if I take either of those numbers and plug it into this function, it will equal 0. Okay, is there anything else to unpack about this whole function notation? One thing that I think is sometimes confusing are these parentheses. Every once in a while I see someone approach f of x or g of x or h of x, and they might accidentally think that this is h being multiplied by x, right, because of the parentheses. Like if I had 5 times 4 written right here, you would say, hey, that's 20. But when I have f of x, that's not f times x. It's a function, and we use the parentheses simply as a placeholder to say, hey, put something there. And if you put something there, that means you're inputting it into the function, then you can compute an output. All right, anyone else want to say anything else about function notation? Anyone think we could have come up with a better name than function? You know, maybe go back 300-400 years ago, like stand up at the math meeting and be like, you know, function, maybe not the best word. Maybe we could choose a different word. Maybe just call it an input-output machine, but that's kind of long. Say input-output machine every time. So, all right. How do you express input-output as a coordinate on a graph or on a table of values? Well, we kind of talked about that already. And as a table of values, we all know a table of values is just a list of coordinates. So this is your input, that's your output. And so let's say you input 2 and you output 9. Then that table of value 2, 9, that really is a coordinate. Okay, consider the function. I make $10 per hour, or a pizza costs $20. Let's look at each of those separately and think of them as a function. So how would I write, I make $10 an hour as a function? And how would I make it as a graph? So first, what would the function be? And you'll notice I went ahead and made it t instead of x. But that kind of gives it away a little bit. So what would our function be? I make $10 an hour.
Time. So f of 10.
Yeah, what would be vision?
Per hour. Oh shit, no, so 10?
T times 10? Yeah, 10t. So my function would simply be 10t. So that function right there represents the fact that I make $10 per hour, because if I only work 1 hour, then I just made $10. And if I work 2 hours, then I just made $20. And that makes pretty good intuitive sense, that however many hours you work, let's say you work a full day, 8 hours, then you just made $80. So there's definitely our function. And then what label goes on each axis? Which one is time and which one is money?
Time would be Time would be the x coordinate.
Yeah, almost always the x-axis becomes time. This is your independent variable, that's your input. And whereas this is your dependent variable, and that's your output. And so when we talk about money, the independent variable is the number of hours I work, right? Because, I mean, theoretically, you have some choice over that. Like, I'm going to work this many hours, and then as a result, I'll make this much money. So time goes here, and then money goes here. Okay, well, I think that takes care of the first one. So I make $10 per hour. The second question says a pizza costs $20. So how can we make that as a function? F of what variable should I use? I think P would be nice. P represents the number of pizzas. So F of P equals what? What would be our function there? If P is the number of pizzas, what do we want to calculate? What? Like, let's say I want 3 pizzas. What would we calculate?
You do 20p.
Yeah, 20p, because we're calculating 20 plus p. Yeah, we're calculating the total cost. We want to know how much is this going to cost us. Like if I say I want 3 pizzas, how much is that going to cost me? So in that case, that'd be f of p equals 20p. And then again, you check. You know, anytime you write down a function, check to make sure it makes sense. So you'd say, well, if I buy 1 pizza, that would be $20. Whereas if I buy 3 pizzas, that would be $60. And so you check, always check to make sure that your function makes sense by throwing in a couple random numbers that you can check and say, well, does that make sense? Okay, so then likewise, what would our graph look like? What goes on the x-axis? Yeah, and by the way, you can always know which goes on the x-axis because it's always your input variable. Whatever number you're inputting, that is your x-axis. So P would go here, and then money again would go here, and that would be our graph. So now that we have these 2 separate things, what we'd like to do is compose these functions. So composition is a particular word, that's what alt check 5 is about. Composition means that you're going to put the 2 functions together to create a new function that incorporates the information from both. So when we do a composition, the question would become, instead of saying, I make, let's see here. I want to diagram this. I work a certain number of hours, and then I make a certain amount of money, but then I use that money to buy a certain number of pizzas. And so what you could end up saying is, I work a certain number of hours so that I can buy a certain number of pizzas. And you just cut out the money altogether. And like, you know, this would be like a pizza is that important to you, that you no longer even think about the fact that you're making money from your job. You just think, okay, how many hours do I have to work so that I can get 7 pizzas? And you just forget about the money, and you just focus on the first input and the final output. So this is what happens in a function composition. You have an input leading to an output, but then that output becomes a new input leading to a new output. And then what you do is you cut out that middleman in the middle and you say, let's just call this the input and look at the final output. And that's what a composition would be. So how would we do it in this particular case? How do we compose these 2? I would like to say that, let's see here, it's going to be, I'm going to plug time into my first function, and then that's going to give me a certain amount of money. Oh, no, I have it written down backwards. Oh, darn. I should have written it the other way around. A pizza costs $20. I had meant to go backwards. Well, I kind of already went down this path a little too far to go back. So I'm just going to stop right there, and we'll consider more examples as we go. But this is what a function composition does. It takes the output of one function and makes it the input of the next function, and then you just create that new function. So let's see, maybe we can just make that function ourselves. Let's say that we want a function of time, so I work some number of hours, that tells you how many pizzas you can buy. So let's just say that I only work 1 hour. Can I buy a pizza yet? If I only work 1 hour, I only made $10, and the pizza costs $20, so I can't buy a pizza yet. But I could buy part of a pizza. How much of a pizza could I buy with only $10? The only half of a pizza. So far what I have is ft equals, and this should be the number of pizzas. So we're going to try to build our function from the ground up. If I work 1 hour, I could get half a pizza. What if I work 2 hours? Yeah, if I work 2 hours, I just made $20, which therefore means I could buy 1 pizza. And so f of 2 equals 1. So again, now I'm saying that this is the number of hours you work, and then the number of pizzas you can buy. So what if I work 3 hours? Then I made $30, so I could buy 1.5 pizzas. So then my output would be 1.5. And likewise, if I work 4 hours, then I would make $40, and then I could turn around and buy 2 pizzas. So we have this new function now, where I'm inputting time, and I'm outputting a number of pizzas. And so what would that function be? What am I doing to these numbers? How does 1 become a half, 2 become 1, 3 become 1.5, and 4 become 2?
What's the ratio of money made per hour to pizzas you're eating by?
It is a ratio. But just very simply, like if you were talking, how do you turn a 4 into a 2? How do you turn a 2 into a 1? How do you turn a 1 into a 1.5? What operation do you do to the number? You just divide it by 2, right? So we could go ahead and say our function is f of t equals 1/2 times t. And that would be our new composed function, stating that for every hour that you work, you can get half of a pizza. Okay, well, all of this is just an example to suggest and introduce this notion of the importance of thinking about functions as input-outputs, and then making the output of one function become the input of the next function, and then creating a new function that goes from the beginning all the way to the end. And that's what we'll be doing. Okay, finally, what does it mean to look at the inverse of a function? First of all, do we use the word inverse in our life?
Yes.
We do? When do we say inverse?
You can use it in business stance because you're looking at the increase of something and the decrease of it.
Oh, so like what's an example of using the word inverse?
Labor in comparison to costs made to a company.
Oh, like an inverse relationship.
Yes.
Ah, okay, very good. Yeah, sometimes we do talk about inverse relationships. That an inverse relationship would be like the more you stay up at night, then no. The less good you'll feel in an inverse relationship.
It works.
What's that?
The less sleep you get, so the increase of less sleep is technically your increase of cognitive
Yeah,
function, or
like here's
increase of
sleep, how much sleep you get, and then up here is your well-being. So if you, well, let's check. If I get lots and lots of sleep, then I would have lots of well-being, whereas if I have little sleep, I'd have little well-being. Well, that would be a direct relationship. How would I say that the other way around? Oh, there are no erasers. I'll have to use my head. Okay, I'm gonna have to run to the next room. To be an inverse relationship, it would have to be the other way around, right?
No,
So-
because inverse is increasing and decreasing and decreasing and increasing, both in a mathematical standpoint and business standpoint.
Inverse would be something like this, where the more you do of one thing, the less you do of the other.
Then
It would have to be,
the better trained an employee is, the less cost it is to a company as a whole. That would be an inverse relationship.
right, yeah, I think so. Okay, so back to the question. The inverse then means, in this particular case, is just running the input and output backwards. So going back to my I don't have an eraser. I'm gonna keep reaching for one. In our original function here that say, yeah, there we go, f of t equals 10t, where my input is the number of hours I work, and and then my output is the number of dollars that I made. If you want an inverse function, you simply reverse the role of input and output. So I would use a special notation that I'd say f to the negative 1. And that little negative 1 there is not an exponent. Like, I realize that we have exponent notation, like x squared means x times x, and then x to the negative 1 means 1 over x. So I know that negative 1 has a well-defined meaning as an exponent. It also means inverse. Now again, go back a couple of hundred years to when the mathematicians got together and said, hey, let's make an inverse function be f to the negative 1. It'd make a lot more sense if they had just written a little I right there, and then we would all agree that that means the inverse of the function. But instead of that, they used negative 1. So instead of inputting hours and outputting dollars, the inverse function would be input dollars and output hours. So that's all an inverse function means. It means reverse the role of input-output. And that's pretty handy. So for instance, in the first case, I'd say, if I work, so many hours, how much money will I make? The inverse function would say, if I want to make this much money, how many hours should I work? And so it's just a matter of reversing the order in which you say the sentence. Okay, these are the ideas that we'll be talking about in chapter 5. So let's look here. Today's March 20th. We're going to look at the beginning of chapter 5. We have 2 days for chapter 5 and then 3 days for chapter 6, and then we'll take a test on chapter 5 and 6. I just posted the notes for chapter 5, 6 on Canvas. So if you wanted electronic copies, or if you want to print out another copy, you can go on to Canvas, go to announcements, and I have an announcement there that says, notes and solutions. Maybe this weekend I'll post some solutions to chapter 5 and 6, as well as the practice test. So you can go ahead and download that and take a look at it. Okay, well, that's where we are. That's what we're doing for the next couple weeks. Anybody have any questions about where we are? Let's see here. I will grade all of your tests by this weekend and post your grades and then give them back to you on Monday. I think that's it. Okay, I have a joke for you. Maybe some of you have already heard this. What do you call cheese that's not yours? Nacho cheese. And then another one. What do you call cheese that you really like? Gouda cheese. Thanks, Josh. That was very kind of you. All right, so preview the unit. Chapter 5 is all about function composition. So again, function composition, we look at that notation right there. It says f of g of x. So when we talk about function composition, what we're really saying is that typically you have a function, and that function, I'll just go back to f of t equals 10t. Normally you just put in a number, like 5, and then that'd be 10 times 5. But other than putting in a number, you can put anything you want into a function. And I remember the first time this happened to me in, gosh, whenever it was, high school or junior high. It blew my mind. Instead of plugging in the number 5, the teacher said, plug in the letter y. And I was like, what do you mean plug in the letter y? That's not a number. I can't compute anything. But all I had to do was just put the y there instead of the 5. So that's one idea, is that into a function, you can plug numbers, but you can also plug letters. While you're at it, instead of plugging in letters, if you wanted to, you could plug in a happy face, and then that would be 10 times happy face. Because that's just how it works. It's just an input, and so you plug it in where the variable was. But more importantly, into a function, you can also plug another function. And in that case, you'd have 10 times g of x. And that right there is what we're looking at. This whole idea of function composition merely means that the input that you're plugging into a function is another function, which is like function inception. Did you ever see that movie Inception with Leonardo DiCaprio? Maybe you did, where in the movie you go to sleep and you start dreaming, and then in your dream you lay down on your bed and you go to sleep, and then you start dreaming, and then in that dream you lay down on your bed and go to sleep and you start dreaming, and it just keeps going down layer upon layer. Well, same thing here. You could take a function, and what could I plug into that function? Another function. And what could I plug into that function? Another function. And what could I plug in? Well, you can plug as many functions embedded within each other as you like, and then see what that answer would be. So that's called function composition. You're plugging a function into a function. Chapter 6, on the other hand, is all about exponential functions and logarithms. So that'll be completely different from chapter 5, other than the fact that exponential functions like 10 to the power of x, and logarithmic functions like log of x, these are technically inverses. The order of input-output are reversed between exponential functions and logarithms. Okay, well, that's where we're headed. So today's chapter 5. We're going to look at functions, function composition, and here we are. Does everybody have this in front of them? I'm going to give everybody a moment to meditate upon anything that you wish to meditate, and I'm going to grab an eraser from another room. Might have to wrestle it out of somebody's hand, but I'll do it. I walked into the next classroom, and they were all in there, very busy. And I grabbed this eraser, and someone actually tried to take it back from me. They said, no, that's our eraser. And I had to grab it and run. Do you believe it? All right. So, look at the top there. Function composition. You can see they have this nice little diagram here, which I implied earlier, that you have x being an input into the f function, and then that's the output, f of x, and then f of x becomes the input into the g function. So the output of the first function became the input of the next function. And instead of thinking of input becomes output and then output becomes input, you just create this new function called the function composition, in which the original input automatically gives you the final output. And so you're taking out the middleman or the middlewoman of the middle step of saying, take that output and make the input of the next function. And you just create this new function called g of f, which goes from the original input to the final output. And that's what a function composition does. And everybody, you might as well write this in your own handwriting. Right up there, they have this notation. It would be very reasonable if we all just use the notation f of g of x. And you'll notice I wrote that a little exaggerated. I made the f kind of big and then the g kind of tiny. I could exaggerate that even more. Oh, now that I have an eraser, I can. So we say things like f of g of x. I normally write that as f g of x. So I call my attention to the fact that I have a single function, f, and what did I just plug into f? G of x. But the notation that books will often use is parenthesis f little circle g parenthesis of x. Seeing that notation for the first time can be a little confusing because at first you look at it and you're like, is that the word fog? But it's not the word fog, it's a little circle. And you're like, well, what's a little circle? Well, we all know the symbols plus and then minus and then times and then divide. But then there's another symbol called a circle, which means function composition. And it means make g the input of function f. Kind of strange because you have to read from right to left. G is the input of f. Right? So that's that notation. Likewise, if you wanted to make g be the original function and plug f into it, then I would write that as big G little f. To remind myself that I'm using the g function and I'm plugging f into it. Then that is given by g circle f of x. So why do we have this extra notation of the little circle? As always, because mathematicians get a little lazy and they just want a new symbol to represent it. Personally, I would just go through life using this notation. But they invented this notation theoretically because why? I mean, if you look, there's a G, there's a G, there's an F, there's an F, there's 1, 2, 3, 4 parentheses, 1, 2, 3, 4 parentheses, there's an X. Literally, this is the addition of a circle, whereas here there was no circle. I have no idea historically why they had this notation. But this is the notation. Okay, so now let's use it. Look at the definition, composition of functions when the output of one function is used as the input of another. So what I would like to do here in these examples for number 1 and 3 is I want to do this function composition and plug in 0, function composition plug in -1, function composition plug in -2, and function composition plug in 1. So let's all try this together. And I'm going to walk us through a series of steps in one way here, and then the next couple problems we'll try it a different way. So in number 1, we're going to do all 4 of those examples. So let's start down that we have f of x equals x squared. And then we have g of x equals 2x plus 1. And in part A, we'd like to know g circle f of 0. The first thing I would do is immediately get rid of this notation and rewrite it as to what that really means. That means g, and what are we plugging into g? F of 0. So g goes first, so that's nice, it stays first. G is the first letter, then g is still the first letter. G becomes the big function into which we're plugging f of 0. Now f of 0, I think we could all just look and find out what f of 0 is. What's f of 0? Yeah, if you input 0, 0 squared is 0. So now I'm going to replace f of 0 with just 0. I replaced f of 0 with 0. You'll notice I just have one long equation that I have going here. It's not an equation, it's an equality. I start with what they want. I rewrite it in a notation that's more user-friendly. I find f of 0, and I know that it's just 0. And now I find g of 0. What happens if I plug 0 into this function? Yeah, 2 times 0 would be 0 plus 1 is 1, and the answer is 1. Now these functions are nice and simple enough that we can just do these inputs in our head. If you wanted to, you could always do some scratch work on the side to say, well, what's g of 0? And you can come over here and say, g empty 2 nothing plus 1, plug in 0, and that means that g of 0 is 0 plus 1, so g of 0 is 1. So if you wanted to, you could go off to the side of your paper and do a little scratch work and confirm for yourself that g of 0 really is 1. There we have it. Okay, let's try B. In B, they want f circle g of -1. Which really means, so again, f is the first function. I write f really big. And what am I going to plug into f? G of -1. So again, kind of think about what's happening here. -1 is the original input. And I'm plugging it into g. And then whatever that output is, that output becomes the input of f. And then we're going to calculate that output. So what's g of -1? If I plug -1 in right here, again, we should all be able to do this in our head. 2 times -1 is -2. -2 plus 1 is -1. So now I replace g of -1 with -1. And now I go find f of -1. So if I plug -1 in right here, -1 squared would just be just 1. -1 times -1 is just 1. Sheer dumb luck that both of those equal 1. Okay, in part C, we'd like f of f. Now this is kind of funny. That means we're going to plug -2 into the f function, whatever that output is, plug it back into the f function. So it's like you're running something through the f function twice. Kind of like putting something in the laundry twice because it's just that dirty. Has anyone ever done that? Run something through the wash twice? Oh man, this thing was really dirty. I'm gonna wash it twice. I have kids. All right, so that means we have f, and into that f we're plugging f of -2. So I go find the first f of -2. So inputting -2, that's -2 squared. -2 times -2 is positive 4. So now I'm plugging in 4 into f. So then plugging in 4 squared is 16, and the answer is 16. How does everybody feel about this? Is this pretty straightforward? Is this like nicer than synthetic division? Is everybody happy that we're like taking a little break from factoring polynomials? All right, so then D, we have f of g, f circle g of 1. And again, by definition, it's big function f. Into that, we're plugging g of a half. So then I go find g of a half. I plug a half into g. 2 times a half is 1, 1 plus 1 is 2. So now I'm doing f of 2. And then I plug 2 into my f function. Input 2, that's 2 squared, which is 4. Okay. Everybody, now that you're done with that, go ahead and try out number 3, technically. Give that a shot, work with your neighbor. I'm just gonna walk around, answer any questions, take a look at your work. So go ahead and try the next one, number 3. And recall some best practices. It's often helpful to write the function empty so you can kind of imagine what you're putting in it. So. That's very interesting. So first one, you have your G first. You're putting it there. But if you write down F, you then would also write down is. You just write F. I see that what you're doing is you're writing down the function so you can see it. The answers. And right now this is correct. Right? So you're doing G at the zero. This one's correct. But right here, this is not technically correct. That's perfect. I would kind of consider that to be your scratch work. We were kind of thinking through it, but we couldn't insert that into your line of these weights out of equal signs. Well, maybe it is. I like that you did that. So here you went ahead and wrote it down. You just read the perfect.
I just didn't see it.
Right. No, and you know what? I'm going to show this on the board. And then from there, you get that one, made that arrow, but then you wrote it down. Yeah, Josh, that's perfect. Yeah, that's very easy to follow. Yeah.
No, that's what I'm taking from.
So, oh, sorry. Yeah, that was. Yeah, the first one we're doing is G of F. So G is the big function, and then F is the inside function. They're putting 0 into F.
Start with this one.
Yep, so you're going to put 0 in. So what do you get if you put 0 in F? 3 minus 0 would just be 3. So it's square.
Right.
So root 3 becomes F of G.
Oh, okay.
Yeah. This is great. Get this out. Oh, hey, I see what you did there. You went ahead and just calculated what it is in decimal. And that's fine, more or less. Like, if you wanted the decimal approximation, then that would be your decimal approximation. But the full answer is 1.73205, and it goes on infinitely far. So what you really want to put right here is root 3. Plus, because your answer is 3.99, the real answer is 4. And that might not seem like a big difference, but if you owe me $4, I don't want you to give me $4. That makes sense. I want you to give me $4, especially if that represented billions. If you owe me $4 million, I don't want you to give me 3.99 million, because then I just lost out on $2,000. I'm not sure. Oh, I see what you did there. You went ahead and put the 0 in there mentally, and that was a root 3. And then you plugged it into that one, and then you got your answer. So this is the correct answer. It just didn't show any of the work that we were doing. Oh, in fact, right here either. I'd like you to show some of the work that we're doing so that you see the step-by-step the formal steps. Yep. Now I see you're getting the right answers, and that's wonderful. But the way you wrote it down here is a little confusing for somebody who's watching it. Like, why did you just do what you did? Whereas writing it down in steps, like I did on the board, like shows the chain of reasoning that takes you from one step. So it's fine that you, I see you know what you're doing, but I really want you to try writing it down the way we do, or at least some of the problem. Okay. Yep. It would look a little awkward, but that's correct.
So far, so good. So you're gonna do G of, well, hold on a second, you're gonna do G of F of 0.
Oh,
So the order of those letters would have to be the same, G then F. There you go. So for F of 0, you're right there, you're gonna plug 0 into that, which is what you're doing right here. So then 3 minus 0 is just 3, and that'll be the square root of 3. And the square root of 3 is gonna replace F of 0. So what you have right here, you kind of wrote down your scratch work, but I would maybe get rid of that right there and write it somewhere else, so that you can keep writing down the steps. Can I demo it? So what do you have here? So getting rid of that F of 0 as well. So this is correct. G of F of 0. That becomes G of F of 0. And then what is F of 0? If you put 0 into F, then 3 minus 0 is 3, that's the square root of 3. So we're going to replace F of 0 with 3. So now that becomes 3. Instead of writing F of 0, you just write 3. Yeah, so far you did that. So you replace the F of 0 with 3. Now you're on the so you're going to square root then at 1. And again, if you want to go somewhere else and do a little scratch work, this would be the function as something squared plus 1. And I'm going to plug root 3 and plug it down. And that root 3 as well. So then you square the square root and that's around, so that's 3. After that, you must do. So that's actually 4. So then that's yes. Yeah, that's a great way of thinking about it. It's a little awkward, right? Because you're plugging root 5 into it. It's just going to look weird. Now let me see the rest of your work. Here's your first one. Yep, very nice. Well, here's your response.
I know.
Yeah, very nice. Yeah, no, it's okay. So then you have that. So that's actually root 5, right? So put a root 5 on. There you go. So you're going to plug root 5 into that, so make that a root 5. And it just won't simplify.
Folks, just so you know, when you get to part C, it'll look awkward. It'll feel uncomfortable, but it's the answer. And I'll explain more when I get up there.
Yeah, so that's it. It's root 3 minus root 5.
And you're going to have a root under a root.
Yeah, just like that. So I see, you know what, I think you're using your own system. And maybe you've done these before. Because the way you're showing your work isn't really the way I did it up there. But I see how you're doing it. Because let's see, for this one. Where do you write the original problem? Well, I don't see this. So the original problem for this one would be this one. So you're plugging it into itself. So you went to here and you plugged in -2.
yes, I'm sorry.
Oh, you wrote it out. Yeah, okay. Well, that's fine. And you know, you're doing what we're going to do on the very end. Yeah. Because then you started with that, and then you plugged in the number, -2. Yeah. Oh, okay. I see what you're doing. Okay, I see what you're doing. It's not the way I was doing it, but I see what you're doing. Whoa. So like for this one, you have G of this is a -1. So put -2. Yep, so you got 2, and then you put 2 in that one. And so 3 minus 2 is 1. And you put 2 into that. Well, I mean, you plug 2 into there, 3 minus 2 is 1, so that's the square root of 1. So technically that's the square root of 1, which equals 1. Maybe you just did that. Okay, yeah. So like then for this one, you have f of x and you're plugging in -2. So you plug -2 into f. So 3 minus -2 is 3 plus 2 is 5. So then, okay, so that's where you put the root 5. So you're just doing all this in your head, right? Yeah. Okay. And then you're going to plug the root 5 into the f function. So then I would start by writing down, you know, the square root of 3 minus something, and then you're plugging in the root 5. Everyone has a call. Oh, really? Okay. So I would try showing the work like I did on the board, where you're going to write a big F, and then into it put G of -1. Nothing. That's just simplified. Yep. Yeah. Little more present.
Okay, folks, let's take a look at these. Now, walking around the room, I saw some variability in how you're showing the work, and that's perfectly fine. You know, my preference is typically that you try writing it down the way I'm writing it down, because I realize that I do tend to give some fairly formal notation, but I think it's helpful notation And I want you to try it at least once. You know, at least once, write down the way I'm writing it on the board. I realize you might have your own system, but part of taking a class is to try something different and to try a new technique, because you never know, once you try it, you might like it. So I'm going to continue writing down my notes here the way I did, and I'd like you to try it that way, but I'll also show some of the techniques that other people in the room did. So for instance, let's look at the first one, part A. We're going to do G of f of 0. So G circle f of 0. So first of all, I just rewrite that, and I say, well, that's technically G, and what am I plugging into G? F of 0. So I'm going to write f of 0. And you know what, maybe just to really contrast it, I'll use a color. So into the G function, I'm plugging f of 0, all right? So now I need to go find, well, what is f of 0? So one thing I saw a student do is they went ahead and went off and found f of 0. So they said, well, f of x is root 3 minus x. And so f of something, I'm going to write it empty, is 3 minus something. And I'm going to plug in 0, so that's 3 minus 0. So f of 0 is root 3. And then they went back and they said, okay, that's what I'm plugging in. So it's G of root 3. So you can see the student used a nice amount of scratch workspace to just go ahead and show their work and find out for sure what is f of 0, it's root 3. So now we have that. So now I need to go find G of root 3. So again, I can take my G function, go somewhere, write it down, G of x equals x squared plus 1. And then write it empty, G of something equals something squared plus 1. And I'm going to plug in the root 3. So now I plug in root 3. And now I can clearly see the square root of 3 squared, the root and the square cancel out. And that gives me G of root 3, which is 3 plus 1. And then that's just G of root 3 is 4. And so now that gives me my final answer is 4. So my only thought, well, I mean, I have a few thoughts, but when I see someone doing a whole lot less work than this, I just get worried that you're doing too much in your head and you're going to make a mistake and get an incorrect answer. I mean, honestly, anybody can make a mistake at any time. I could have made a mistake in this process, and I'm showing tons of work. But it's always more helpful to show your full chain of reasoning. And then ultimately, this is what your work would look like. Right there. That row of steps right there, where you say, by definition, this is what they want. I rewrite it according to a more friendly notation. I go find f of 0. I did. It's root 3. I replace f of 0 with root 3. Now I go find g of root 3, which I did, and then I replace it with 4. So that really would be the ideal notation that you would expect to see in a textbook, and that you'd expect to see other people kind of publish in a, on a website or in a textbook. So part of my goal is to familiarize you with that, to see that notation. Okay, so there's part A. So let's see, I'm going to go over here to do part B. So in part B, we wanted f circle g of -1, which is really f, and what am I going to find? G of -1. So what is g of -1? Again, you could go somewhere and do a little scratch work. If I want g of -1, that means I'm going to plug -1 into right here. So -1 squared is just 1, and then 1 plus 1 is 2. So now I know that g of -1 is really 2. Is that what everybody got? G of -1 is 2. Okay, so now I go off and I find f of 2. So now I run on over to my f function and I plug in a 2. So now I have 3 minus 2, which is 1, and the square root of 1 is just 1. And so that'd be my final output. Overall, I know that I tend to show lots and lots of work, but that's not a ton of work. That's just the original problem, rewriting it by definition, finding your first output, and then finding your second output. All right, part C. C was a little awkward. In part C, we're looking for f of -2. So that's the problem they gave us. Now we're going to rewrite what they want us to find. F is the first function, so I write it nice and big. And into that, I'm plugging in f of -2. So now we need to go find f of -2. So again, you go back to your f function and plug in a -2. What happens if I plug in a -2 right here? It's 3 minus -2. So it's really 3 plus 2, which is 5, and that's root 5. So that output is root 5. So I replace f of -2 with root 5. It's still sitting there waiting to be plugged into the function f. So now what? I have to plug root 5 into the f function. This one looks a little awkward. If I put root 5 right here, I really have the square root of 3 minus root 5. And that doesn't simplify at all. You just end up with the square root of 3 minus root 5. But once again, that's kind of like root inception. You've got a root inside a root inside a root. Well, just a single root inside of a root. But that's it. That's just your answer. The square root of 3 minus root 5. All right, and then for part D, we had f circle g of 1/2. So again, by definition, that's the f function. And what are we plugging into it? G of 1/2. So then you go off and you find g of 1/2. So if I plug 1/2 into g, right here, I'm going to plug in 1/2. So that's 1/2 squared. What's 1/2 times 1/2? You have 0.25 or just 1/4. And then 1/4 plus 1, well, probably easier is 0.25. 0.25 plus 1 is 1.25. So now I have f of 1.25. And so now I run off and I find out what happens if I plug 1.25 into f. So I go back to f and I plug in 1.25. So 3 minus $1.25 is $1.75. So that would just be the square root of $1.75. And there we have it.
So
Now, yes?
for D, do you want us to solve for the square root of 7? Just leave it as root 1.75.
Yeah, that's a really good question. Like for instance, this, you could have also solved as a decimal, by typing it into your calculator. This, you could also solve as a decimal by typing it into your calculator. In fact, 1.75, that's really, what, 7/4? Yep. And so, I mean, even that, you can split into root 7 over root 4, and the square root of 4 you can actually do. So that'd be root 7 over 2. So that's another way you could have written the answer. Instead of root 1.75, you could have had root 7 over 2, or you can plug the whole thing into your calculator and get a decimal. So here's a thought about decimals. So I'm going to take this one, for instance. Root 3 minus root 5. Let's see what that is. That'd be the square root of parenthesis 3 minus the square root of 5, parenthesis, parenthesis. And I got the answer 0.87403.20489. Is that the answer? I mean, I'm the one who looked at my calculator. But is this what that equals? Do you feel like I'm asking you a trick question? I do sometimes ask trick questions. That is not the answer. The answer has infinitely many decimals. I just cut off infinitely many decimals from the accuracy of my answer. Do you know what this answer is? This answer is a lie. That's not the answer. That's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimals out of infinitely many decimals. So you could say this is an approximation. I prefer to call it a lie. That's not the answer. This is the answer. This answer is exact. This answer is merely approximate. And, in the long run, if you're just talking about this is how much money you owe me, well, how much money do you owe me? You owe me 87 cents. Okay, so that's not a lie anymore. You owe me 87 cents. But if I actually wanted to know what that number is equal to, it's not that. So Chelsea, I don't know if I answered your question exactly, but this is always the better answer. We only ever turn it into a decimal if we need to do some sort of practical application where, like maybe this is how long of a piece of wood you need from Home Depot. So you would convert that into a decimal and say, hey, I need a piece of wood measured to be 0.874 meters. And then you'd walk into Home Depot and say, hey, this is how long of a board I need. Whereas if you walked into Home Depot and you said, hey, I need a board that's root 3 minus root 5 inches long, they would throw you out. What are you even talking about? Okay. Well, folks, that was our first look at doing function composition. And again, I really hope you wrote it down in this notation just to try it at least once. So if you turn the page, we're going to now look at function notation where there's no number to input. We're just going to build the new function. We're just going to build the new function. And we'll do the first, let's see here. Where can I go? I'm going to go here. All right. So we're gonna start with number 5, and I've got my 2 different functions, and we're gonna find all of those. We're gonna find g of f of x, f of g of x, and then f of x. So let's start number 5. I'm gonna go ahead and write down what I have. And folks, do this with me. Even though it's sitting there on your page, I know it's already there. But write down the function, and then write it empty. F of equals 2 something plus 3. And then g of, I suppose you don't have to write the function again, but write it empty. G of equals something squared plus 9. It's a really powerful idea to write functions empty, because what you're writing down is the structure of the computation. So those are the functions we're dealing with. And in number 5, what they want us to find for part A is g circle f of x. You can say g circle f, or you can just say g of f. That might feel a little confusing because if you just look right there, it looks like the word of. But that is, in fact, how you pronounce this, g of f of x. It's a lot of ofs, of. Okay, so what are we going to do? We start with our notation, and just like before, we say we're doing the g function, and we're going to input the f function. So now here's what we're going to do. The first thing we're going to do is look at the big outside function, which is g, and write down g nice and big and empty. What's our g function? Something squared minus 9. So write it nice and big. Something squared minus 9. And what is it that we're inputting into that function? F of x. So that to me would be step 1. Is we're saying the definition of g circle f is really g as the big function and f as the function you're putting into that function. And so I'm going to take g first and write it nice and big, something squared minus 9. And as before, we're going to plug in f of x. But then, instead of writing f of x, so again, I have my something squared minus 9. Instead of actually writing f of x, write down what f of x is. F of x is 2x plus 3. And that is the function composition. We have essentially plugged f into g. So I wrote g nice and big, and then I plugged the f function into it. Now this right here, you could call it done. You can say, all right, well, there we go. That's my function composition. But, you know, if you wanted to give this function to a friend or your boss, what would we do to it? You want to simplify it out. So we're going to go ahead and FOIL it. So you would take that and say 2x plus 3 times 2x plus 3, and then minus 9. So we'd FOIL. So first, 2x plus 3, or I'm sorry, 2x times 2x, that's 4x squared. And then outer, 2x times 3 is 6x. Inner, 3 times 2x is 6x. And then last, 3 times 3 is 9. Minus the 9, ooh. See, that's nice. That's one reason why you always try to simplify things, because you never know what might cancel out. The 9's canceled out. So now we have 4x squared plus 12x. And that's kind of nice.
That would be the point.
It could be. It depends on how much you like the person you're about to hand the function to. Right? So if you like the person you're about to hand it to, you can even go one step further. What can we do to this? Yeah, you can factor out a 4x, and then you've got 4x outside of x plus 3. So to Josh's question, that could be your final answer, or that could be your final answer. It really just depends on how much you like the person who you're giving your final answer to. If you say, well, I don't like that person at all, I'm not even going to do it. But no, you like the person at least a little bit. You like the person enough to do the problem, and then you like them enough to simplify it as much as possible. Okay, so what did we just find out? By plugging a function into a function, I want to show you this drawing again. See, we're looking at g of f of x, which means that if you have your original input, okay, the original input going into f, look at your original input. The original input is that letter x right there. First it goes into f, and then that output goes into g. So if I start with an original input, x, I'm going to plug that into f. and that gives me f of x. And that would be my output, and I would be done. Except I'm now going to take my f of x output and plug that in as an input into the g function. And so now I have g of f of x. And that's what we're looking for from the beginning, g of f of x. So I took my x input, I plugged it into f, that was my output, but then I turned around and considered that my input of a new function, and that gave me g of f of x. And if you look, the original function, f of x, was 2x plus 3. And then my original function, g of x, was x squared minus 9. But now what we can do is completely bypass that middle step and just call this the function g of f of x. And we now know that that answer is 4x squared plus 12x. That's what we've accomplished, is instead of doing one input and then take that output and treat it as another input, we've simply created one function where the original input goes into it, and whammo, you skip right to the end. So it's like a time-saving device. Instead of doing input and then input again, you just have one function, you plug in the input, and it goes all the way to 10. So I hope that's compelling as to why we would do function composition. It's turning a two-step process into a one-step process. I say a two-step process into a one-step process. You're like, I don't know, Mr. G, it took us like 5 steps. But see, if you were going to do this process over and over again as your job, you wouldn't want to sit all day long doing a two-step process when you could just do a one-step process. Okay, so what we just accomplished then was part A. So now let's try part B and part C. Now, once again, I say this very kindly, professionally. Please write down exactly what I'm writing down. I know that a lot of you might have your own techniques that you've used in the past, but I really want you to try this technique. So we're looking at number 5, and we're doing part B. And what we're looking for is F circle G of X. That's what we want. We'll finish these problems and then we'll take it. So first, by definition, and again, exaggerate with your penmanship. I'm going to write down the f function nice and big. And what am I plugging into the f function? The g function, which I'll write nice and tiny. So into the f function, I'm plugging the g function. So now, my f function, the one that I wrote nice and big, I'm going to write that one down first, empty. So where did that go? My f function is 2 something plus 3. So that's 2 something plus 3. That's my f function. And into that, I'm plugging in the g of x function. Now, if you'd like, we don't have to bother writing g of x right now. We could actually go find what g of x is. G of x is x squared minus 9. So into that, I will write x squared minus 9. And that right there, you could just kind of stare at and meditate for a while and allow your eyes to see the visual impact of the 2 something plus 3 I wrote right, real big. That's my f function. And then the x squared minus 9, I'll even write it smaller, is what I'm plugging into that function. So when we look at f circle g, that is f of g of x, the g of x is being inputted into the f function. So I make f nice and big, and I plug in g of x. Now this one's a little easier to simplify. Like now, if I unexaggerate my typeface and just make it 2x squared minus 9 plus 3, then I can just distribute, and that gives me 2x squared minus 18 plus 3, which is 2x squared minus 15. Now, by all means, that would be the end of that particular problem. But because you're all an inquisitive philosophical group, and I'm sure you'd like to see, like, well, can this be factored? You don't have to write this down, but just for fun, look. You could factor out a 2, couldn't you? And it'd be x squared minus 7.5, if you really wanted to. And then this is a difference of squares, except that's not a square number, but you can still use that factoring technique to say x minus root 7.5 and x plus root 7.5. And you might say, gee, that's crazy. Erase that. But you'll notice now I factored it, and now I know the x-intercepts of this graph. Right? Do you all remember us going over that that if it's x squared minus 25, that's definitely a difference of squares, and you can say x plus 5, x minus 5. But the real rule is simply x minus root 25 and x plus root 25, where you're just putting a root symbol over whatever that number is. And in this case, the root 25 simplifies to 5. But if you have anything like x squared minus 7, you can call that x plus root 7 and x minus root 7. Recall that? We did it in class, didn't we? Yeah. Okay. So again, even though you don't have to go that far, you don't have to go that far. But the fact is you could. And then you'd be factoring a polynomial just like we did, and you'd know the x-intercepts. Okay, let's try one more. C. So in C, we want f of x. Which again, it's kind of fun. You're plugging the function into its own self. Like the Ouroboros, the snake eating its own tail. Have you ever seen that picture of a snake eating its own tail? So we're plugging f into f. So here's my f function, and what am I plugging into it? F. I admit this is enough to kind of hurt the brain a little bit. So we're going to write the f function nice and big. The f function is 2 something plus 3. And what am I plugging into it? The f function, which is 2x plus 3. And so then we distribute. So that would give us 4x plus 6 plus 3, which is 4x plus 9. And that's the composition function. Very nice. Oh yeah, so see, I just did the thing that you were doing on the first page. So folks, do you remember doing function composition before? Is this something that rings a bell? Maybe? All right, well, let's take our break. The time is 9:04, let's come back at 9:14. Oh, wonderful. Oh, hey, folks, during break, as in right now, or if you want to go take a break and then do it at the end of class, I'd like to go ahead and collect all of your work from chapters 3 and 4. So I need your practice test, preferably on top, followed by your chapter 3 notes and your chapter 4 notes, and we can all make a nice little stack right here. Either bring it now during break or bring it up at the end of class. Is this good? So I left my copy here a long time ago. I'm really sorry if you guessed this. Did either of you want to go ahead and have a sip since it was here? Yeah, okay. Then I'll bring it back. All right, folks, let's try number 7, so we can all see one more example of how this works. We'll move on. So in number 7, we have 2 new functions. And we'll start by writing them down. I hope that you all write them down as well. I realize they're already there, so at least write them empty. So I've got my f function, which is 3 minus x squared. So I'll write that as f of something equals 3 minus something squared. And then I have my g function, which is the square root of something plus 1. So I'll write g of something equals the square root of something plus 1. Again, this is called writing it empty, using a parenthesis everywhere there was a variable. So we're going to do part A, which is g of f of x. So again, it goes in order. So g is the first letter, so we write that nice and big. Our g function is root something plus 1. Oh, you know, I suppose I could have written the definition first. The definition is g of fx. That's the definition. Never hurts to write it down. And then I write down the g function as is big, so that's something plus 1. And then inside of that big g function, I write the little f function, which is 3 minus x squared. Now, sometimes you do a composition and it simplifies a lot. Sometimes you do a composition and it doesn't simplify a lot. So in this case, I have 3 minus x squared plus 1, so that's going to be 4 minus x squared. And that's it. It's the square root of 4 minus x squared. And that's your composition. Just to note, you know, in lines with keeping up our practice with doing factoring, notice this one. We have the square root of 4 minus x squared. Maybe you looked at the 4 minus x squared and you're like, hey, that's a difference of squares. So I'm going to rewrite that as parenthesis, the square root of 2 minus x, 2 plus x. And then furthermore, I can break that root apart into 2 roots, and then my function would be the square root of 2 minus x times the square root of 2 minus x. And so once again, what I've accomplished is factoring. Right? This particular factoring is not just a parenthesis, there's a square root in there. But you'll notice that if I did want to find the x-intercepts now, I set the whole thing equal to 0, and I have a product rule. I have this times this. So I could set each of those equal to 0, and I'd have root 2 minus x. Oh, one of them should be plus x. Set that one equal to 0, and then root 2 plus x. Set that one equal to 0. Square both sides, and I have 2 minus x equals 0, or x equals 2. And over here, square both sides, and I have 2 plus x equals 0, or x equals negative 2. So by taking that one step further, I now did find my x-intercepts. And I can draw my graph, and I can say I have an x-intercept at 2, and I have an x-intercept at negative 2. All right? I definitely went way further with this problem than I had to. I just wanted to loop it back to what we have been talking about, which is the ability to take a function, set it equal to 0, find the x-intercepts, and then take a look at the graph and see what the x-intercepts would look like. In fact, I'm going to go one step further with this. This function is not a polynomial because there's a square root involved. Let's just take a look anyway. What was our final answer? The square root of 4 minus x squared. Oh, there we go. There. So that's what our function ended up looking at. And did we have x-intercepts at 2 and negative 2? Yeah. And it turns out that this is half of a circle. It's a semicircle. So it's just the top part of a circle. If I wanted the bottom part of the circle, I would do the negative square root of 4 minus x squared. And then I would have the whole circle. And so this particular function, when you compose it, now see, this is really interesting. Look at these two original functions. The original function was 3 minus x squared. That's an upside down parabola. The other original function was the square root of x plus 1. So let's look at these in turn. The first function was an upside down parabola. The next function was a sideways parabola. And when we compose an upside down parabola with a sideways parabola, the result is a circle. Isn't that fun? Isn't that interesting? At the very least, that's interesting. That you can compose two completely non-circular functions, and by composing them, you end up with a circle. That's kind of the underlying message of this unit, is you can take simple functions, compose them to make more complex functions. Okay, so that was part A. Everybody? Part B. So now we'll do f of g of x. So everybody go and try that out. F of g of x. Start by writing down the definition. That's big F, little g. And everybody try that out. Let's see what you end up with. Oh, goody. Thank you, everybody, for bringing up your papers. If you didn't get to do it during the break, you can bring it up at the
in class. Oh, right, yeah, because this one is looking at it now. So, how are you gonna simplify this? What happens when you square it? No, does that square root line go all the way over there? Okay, there you go. And what happens when you square it? Yeah. Very nice. So you split the root. This way. Okay. Oh, so you plug it into that. So instead of writing that, so you have parts of what we have, right equals n. Okay, so the first thing we're going to do is write the f function nice and big. So you're going to write 3 minus parentheses squared. 3 minus parentheses squared. Big parentheses. So you have that stuff. Okay, very good. So that's the f function. Now plug in the g function into that as a parentheses. That's how we do that. This is 3 minus. Yeah. There you go. That's perfect. That's exactly right. So you plug the g function into the f. Now you can just simplify it. So when you square root, cancel, and you can go on to the next step.
Okay, folks, let's compare answers. We're doing the f function first, nice and big. That's 3 minus something squared. So 3 minus something squared. And into that, I am plugging the g function, which is root x plus 1. So root x plus 1. And what happens when you square a root? They cancel out. And now we have 3 minus, and here you want to be very careful. It's 3 minus x plus 1. Anytime you're doing subtraction, you want to make sure to put the thing after it in parentheses so that you make sure to distribute the minus. So we're going to distribute the minus, and that gives us 3 minus x minus 1, which would really end up with 2 minus x. So that's the function composition f of g of x. Now when we go to do the last one, which is f circle f of x, so f of x. Again, that's f is our big function, and what are we plugging into it? Itself. So I'm going to start by writing f really big. So my f function was 3 minus something squared. And then into that, I'm going to plug the f function, which is 3 minus x squared. Now, again, right there, you could call it done. If you're in the Moore system doing your homework, it'll accept that answer. It'll take that answer. However, you know, again, depending on how much you like the person who you're giving the answer to, that answer could clean up significantly if you go ahead and FOIL it out. So I do want us to go ahead and FOIL it out just to see what it looks like, because oftentimes, you know, it's kind of a gamble. You might say, nah, just leave it. But sometimes if you FOIL it and simplify it, you end up with something even better and less complicated than that. So let's try it. If we have 3 minus x squared, first we're going to have to FOIL 3 minus x squared times 3 minus x squared. And I'm even going to go an extra step, put that whole darn thing in brackets, so that I remember that I still have this 3 minus waiting to distribute to whatever is inside of there. So now I'll go ahead and FOIL all that out. So first 9, outer minus 3x, inner minus 3x squared, and then last plus x to the 4th. So now I have 3 minus, big bracket, 9 minus 6x squared plus x to the fourth. And now I can go ahead and distribute the minus to all of those three terms. And I end up with 3 minus 9 plus 6x squared minus x to the fourth. And then ideally, we'd want to rewrite all that in order with the highest power of x first. So it'd be negative x to the fourth plus 6x squared, and then 3 minus 9 is negative 6. And then, you know, did it clean up nice? I mean, it's not the cleanest expression I've ever seen, but that would be the final answer. Questions or feelings about all of this? Writing the big function and then writing a little function inside of it? Those were our main examples of doing computation-heavy, lots of work to get at your answer. The next couple of problems that we have is simply a matter of looking up your answer from either a list of coordinates or a graph. Now keep in mind, a list of coordinates is a graph, and a graph is a list of coordinates. I really want to make sure that everybody feels very comfortable seeing that and thinking of that immediately. Like a list of coordinates is a graph, and a graph is a list of coordinates. So before we dive into the problems, 9, 10, 11, 12, let's look at those list of coordinates that they gave us and think about what it really represents. Because sometimes if you just look at that and you see f equals curly bracket, all those coordinates, you look at it and you get a little dizzy, maybe you fade out a little bit. You're like, oh, what is that? What am I even looking at? Let's skip this problem and come back to it, right? So what does that even mean, f equals, and then a big long list of coordinates? There's two ways to look at that. You could say that that's actually a table of values. Right, so I have a table, so if I input -3, I get 4. If I input -2, I get 2. If I input -1, I get 0. If I input 0, I get 1. If I input 1, I get 3. If I input 2, I get 4. If I input 3, I get -1. Right? So I just translated the information they gave me into a slightly more user-friendly manner. Like maybe you've never even seen that notation before. F equals curly bracket, all those input outputs. But remember, a function is just an input-output machine. And this curly bracket means, hey, here's a set of input outputs that were generated by this function. So now I wrote them down as a table of values, but now I'm going to write them down as a graph. So now in my graph, I would go 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 4. So now this is -3, 4, -2, 2, -1, 0, 1, 3, 2, 4, and 3, -1. Okay, so is that thing a graph? I don't know. But can you imagine connecting the dots into a nice smooth polynomial shape? Perhaps. Perhaps what this thing looks like is bounds, slice. Anybody think? Could be. Fact is, we don't know. Fact is, we're completely ignorant about what the rest of the graph looks like. They only gave us a few coordinates. But we could connect the dots just for fun, or we could just not connect the dots and just know that's where our coordinates are. But the key thing we want to remember is that we have a list of inputs and we have a list of outputs. And we have the same thing now for G. So if I go ahead now and I look at G, and I say my G function is this list of inputs and outputs, which is -3, -2, -2, 0, -1, -4, 0, 0, 1, -3, 1, and 3, 2. Now, once again, I can make myself a nice little graph because a list of coordinates is a graph, and a graph is a list of coordinates. So now I would have But folks, as I'm sitting up here doing this, I realize I'm like, well, this is taking a while. Oh, you know, writing down the list and then making the graph is taking a while. Everybody's, you know, they're sitting there watching, it's taking a while. But it's fine. Math takes time, right? Like, this is a good idea. One of the first things you could do when you see some new information is to translate it into a language that's more user-friendly to you. You know, take a moment. Get to know what you're looking at. Just rewrite it in a couple different ways and look at it, because that could help you solve the problem. Okay, so now here I've got -3, -2. I'll make blue dots this time. -2, 0, -1, -4, 0, 0, 1, 3, 2, 1, and 3, 2. There we go. So once again, what does this graph look like? No idea. We have just no idea. It could look something like bounce, bounce. It could look like that. But we don't know because it's just a few points that they gave us. It could look very different from that. But now we're ready to actually solve some problems. So everybody, now that we've seen how to express that data in different ways, let's look at f of g of 3. So what does that mean? We want, I'm going to write it vertically this time just to show it in a different way. We want f of g of 3. So what's g of 3? And it might help if you look at that 3 and remember that 3 is an input into the g function. Oh. Whoa. Somebody, who was that? Nice, Josh. So we're going to look over the g function, input of 3, and the output is a 2. So I can find that here by looking at my list of table values. You could have looked at the original list. I go to the g, and I input a 3, I output a 2. So now I know that that whole g of 3 right there is just a 2. And I could have seen that on my graph as well, right? 3, my input's 3, my output's 2. So now I go find f of 2. So again, you can go anywhere. I can look at my f table of values, I can look at my f graph, I can look at my f list of coordinates. I know I want to input 2. So I can find that right here. My input is a 2, my output is a 4. I can look at my table of values, my input is a 2, my output is a 4. I can look at my graph, my input is a 2, my output is a 4. Either way, the answer's 4. Now, by showing you 3 different ways to look at these values, these data values, I certainly did not intend to confuse you. Right now, you could be looking like, oh my gosh, we got the things on the paper, we got the table, we got the graph, this is so much to look at. Just choose whichever one you like best. You know, choose what is most comfortable to you. And just be aware that there are other ways to look at it. So now how about, oh, that was number 9. Number 10. So number 10, we have f of 0. And so that's going to be f of 0. So what is f of 0? Yeah, we can go to our table. If I input 0, the output's 1. If I go to the graph, if I input 0, my output is. Did I not put that? I didn't even put that coordinate on there. There we go. There we go. Or I can look at the original set. So if I plug in 0, I get 1. Either way, I have f of 1. So now once again, I go look up f of 1. I could do it on my table of values, input 1, output 3. I can look at my graph, input 1, output 3. I can look at the original list, input 1, output 3. The answer is 3. So everybody, go ahead and do 11 and 12. Yeah, very well. So let's see what happens. Yeah. Number 11 is a trick question. You might be looking at it thinking, how am I supposed to look that up? What's that, Josh? It's already marked. Oh, yeah, that's true. Yeah, you'll notice that one is already in the user-friendly notation. It's going to help you a lot later on if you have all this stuff. Because when you just write the number down. Well, I realize quick, you just do it all. Oh, yeah. Okay. But still later on, when you go to kind of review or study the test, it'd be helpful to see some steps. Yeah, very nice. That's exactly right. And then there is no 4. So.
So we look up -3 0 to the back, which is there. So input -3. No, because we're looking at f of -3. Yeah, that's the one that we're looking at first.
Okay.
Yeah, in fact, something you know,
This one here.
highlight, that's the answer you're going to look for.
This
The f of the input
one.
-3.
This one.
So now you replace that whole thing with 4.
So
So then
you
it's g from
so that's why we want the F on the F. That means
Yeah, there you go. And then g of 4, you go to work out 4.
that's function of that.
So this would be undefined.
So you just find whenever it gets so 0.
So you look at, so you plug in 0 into f. So the input is 0 and output is 0. So now that whole thing is replaced with negative
The first 0.
You look at f and you go 1. So then you
So you have to plug in that 1 instead.
All right, folks, let's try number 11 and 12.
It's easier to see when we do it.
So in the first thing we're looking for is f of -3. And maybe by underlining it, it draws your attention to that fact. That your first input is -3, and the first thing you're plugging -3 into is f. So we go look up in f, input -3, output 4. And so I'm just going to replace that whole thing, f of -3, with 4. So now I go to look at the g function, and I don't have an input of 4. So what would I say about this? Yeah, you can say, I don't know. Right? It's not listed on the table. And this is a literal example of the word undefined. It is undefined. They did not define it for me. They did not include it in the definition of G. The definition of G did not include an input of 4, and therefore it is not defined. It is undefined. We have no idea what G of 4 is. Our graph doesn't go that far. We don't have a table to tell us. There could be an answer. We're just ignorant. So we wouldn't say 0. We would just say we don't know. It's undefined. Okay, and then in number 12, we're doing G of 2. So G of 2. I need to go find G of 2 first. So input 2. Oh, there it is. Oh, thank you. There we go. So we're going to input -2 into G. So if I input -2, the output's 0. So now that becomes G of 0. And then if you input 0 into G, the input is 0, the output is 0. So that whole thing just becomes 0. You know, to a certain extent, we haven't done a lot of solving today, have we? Like, we've not really done any algebra. I mean, I've done a little algebra kind of for fun over here. But we didn't solve for x. We didn't really solve for any x-intercepts. We're just plugging numbers into functions and seeing what you get. That's all we're really doing. Okay, so now you'll notice 13 through 16, they give you the graph, which a graph is a list of coordinates. So just for fun, I'm going to take that first graph and I'm going to rewrite it for you so you see that you could rewrite it if you wanted to as well. So like looking at my graph y equals f of x, I could go ahead and make my table of values for f of x. I'm just going to read the coordinates from left to right. My first coordinate is input 0, output 4, input 1, output 2, input 2, output 2, no, 3, input 3, output 3, and input 4, output 0. Now, big question, does everyone see where I got those numbers? Because the x value is always the input and the y value is always the output. So when I look at this first coordinate way up here, my x value is 0, my y value is 4. So the first coordinate is 0, 4. And then when I look at this coordinate, the x value is 1 and the y value is 2. So that's the coordinate 1, 2. And look at this coordinate, the x value is 2, the y value is 3, so that's the coordinate 2, 3. And this coordinate, the x value is 3 and the y value is 3, so that's the coordinate 3, 3. And this coordinate, the x value is 4 and the y value is 0, so that's the coordinate 4, 0. So just for fun, I changed the graph of f of x into a table of values. And then equally for fun, I could turn that table of values into a list. F is the set of coordinates 0, 4, 1, 2, 2, 3, 3, 3, 4, 0. And to which you might say, Mr. G, you don't have to do any of that stuff. Let's just solve the problem, right? because they just want us to go look up answers. But I just thought it'd be nice to show that you could rewrite it in different ways. But we are going to practice just reading the answers off the graph. So take a look. This is a little, a little tricky on the brain. I'm going to erase all this. Give myself some space to work right next to the board. And let's take a look at 13. That's G, circle F. Now, always for me, the first thing I would do is rewrite this in a user-friendly way, which is big G, little f. So the first thing we're going to do is go find f of 1. So I go to my f graph, I input 1, and my output is 2. So when I want to find f of 1, I go to my f graph, I input 1, the input's always the x-axis, and I output 2. So now that's g of 2. Now I go to my g graph, and I input 2. So again, input is on the x-axis. I input 2 on my g graph, and my output is 3. And even though you could turn that graph into a list of coordinates or a table of values, I would really like you to practice just reading the information off the graph. So in the case of 14, we have f, so g 3, and rewriting that as big F, little g of 3. Then you go look for it. So tell you what, I'm just going to write these down, and I'm going to walk around the room and make sure everybody feels good about looking this information up on the graph. So this would be your work setup. This would be a nice way to start each problem. And then go look up the answers on the graph. Yeah, you did. Great. How did it go? Did it make sense?
Yeah.
Good. Let's go, nice. Good. Yeah, we'll definitely start by rewriting it. Yeah, very good. Did it work, Josh? Okay, the f of g, so f of g 3, which is 0. Yep. And then we plug in 0. Yes, very nice. Did you find that helpful to rewrite it as a kid?
Yeah, I think the table of just get mixed up.
Yeah, this is kind of weird notation. I don't know of anybody who writes it like that, but the table is pretty nice.
Yeah, I like it.
Yeah, there you go. Very nice, Isaac. So then g of 3, you go to the g, the input is 0. Oh, and then you went straight over there and the input is 0 to get 4. Oh, so you just did all that in one step.
Yeah.
Okay, a little dangerous, a little risky to do it all in one step. I think it'd be nicer to do it in 2 steps, but very nice. How did that feel, though? Is it working? Okay. Great. Looking good. Nice. Let's go, man. Very nice, Eric. Looking good. Looking good. Super. Nice.
It's just give you a list of questions. So you could just algebra.
All right, folks. Walk around the room. You're all progressing. I'm just going to jot in our answers real quick then. So g of 3 would be 0, so that's f of 0. And then f of 0 would be 4. Now, some of you, I noticed, you skipped this step. And you just did the whole thing, right? You just did the whole thing kind of in your head. You said, okay, well, I'm going to plug 3 into g. So I plug my 3 in, that's 0. And then I go over and plug 0 into f, and you get 4. And you know, if that feels comfortable to you, that's wonderful. You know, I think it's a little risky. I think that you could accidentally make a mistake that way, but it is possible to just use your eyes to look at the graph and read those answers off. It is possible. It's just risky, that's all. Like texting and driving. You can do it, but it's risky, right? Okay, so the next one, I'm going to plug 1 into f twice. So I plug 1 into f, I get 2. I take 2, I plug that into f, I get 3. So sure, like I just did, you can just do the whole thing visually. Plug 1 into g twice. So I plug 1 into g, I get 3. I take that 3, I plug it into g, I get 0. All right. Okay, so that's function composition, input, output, how to compose two functions to get more interesting functions. Now 5.2, we're going to talk about inverses. Now, again, the best definition of inverse you can use is that it switches the role of input-output. We're simply switching the role of input-output. And I'd like you all, if you would, to do a nice little example with that, with me on just the margin, just over there on the margin. We're not necessarily going to read through all of these definitions together. I'm going to give you definitions as we go, but on the margin over there, let's take a look at this. Let's say you had the function f of x equals x squared, and build a little table of values. So input, output, I'm going to input 0, 1, 2, 3, and that's it. So, very basic idea, we've got a function, x squared. I'm going to input 0, 1, 2, 3. So my output would be 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. So if you want an inverse function, all that is necessary is I can go ahead and tell you right now what the inverse of this function is. It would simply be a table that looks like this. 0, 1, 4, 9, 0, 1, 2, 3. That is the inverse, because I just switched the roles of input-output. Instead of inputting 3 and outputting 9, I'm inputting 9 and outputting 3. And that's it. That's the definition of inverse. It's swapping the role of input and output. Now, what would that function be? So again, I'm going to use this notation, f to the negative 1 of x. And again, very unfortunate, f to the negative 1, it looks like x to the negative 1, which means the reciprocal. But really, the negative 1 in this case means inverse. So again, this is just my own beef with society. It should be f little I, but they don't do that. They use a negative 1. So just know that f to the negative 1 actually means inverse. You do not say f to the negative 1 of x. You say f inverse of x. That's how you read it. F inverse of x. Okay, so what would the function be? How could I take the number 0 and get 0, take 1 and get 1, take 4 and get 2, take 9 and get 3? What would that function be? Yeah, just the square root of x. So we now see two examples of what it means to write an inverse. An inverse is when the table of values, input, output, the roles are reversed. Literally, you swap the columns so that your output now becomes the input, and your input now becomes the output. And furthermore, here's a nice example of two functions that are inverses. X squared and square root of x are inverses. This is a nice example because that tells us something we already knew. That let's say you wanted to solve the problem x squared equals 16. How do you solve the equation x squared equals 16? You square root, right? And that's because squaring and square rooting are inverses. They cancel each other out. So by square rooting both sides, it cancels. That's the second thing inverse means. Inverse means that you swap input-output, but inverse also means that inverse operations cancel each other out. And so what are all the inverse operations? Inverse operations, now this is an inverse operation. Inverse operation would be plus minus, times divide, square root. And when you get to calculus, derivative, integral. Okay, so those are all inverse operations. They all cancel each other out. They're simply operations that cancel each other out. Such that if you were doing algebra, you could use one or the other of them to cancel something out from your equation and solve for x. So that's one thing inverse means. But for our sake, inverse means switching the role of input-output. And then our goal will be, if you know one function, how do you find the inverse function? This one was pretty easy because you just thought of the opposite of squaring, which is square rooting. But in general, it's a little challenging to find an inverse function. And there's a couple different ways to do it, and we're going to review all those ways. All right. Okay, so let's look at example 1. Show that the given function is 1-to-1 and find its inverse. So let's talk about a couple of things. First of all, you recall the definition that we gave of a function by looking at the graph? By looking at a graph, how do you know if something is a function or not? What's the rule for a graph being a function and then a graph not being a function? Yeah, it can't have two y values for the same x value. and looking at a graph, we called it a particular test. It was called the, well, the one we did before was the vertical line test. Yeah, so here I can draw any vertical line and it only touches the graph once. You know, it only touches it once. So this is a function. Whereas here, if I draw a vertical line, it touches it twice. No good, not a function. Admittedly, it only touches it once here, but over here it touches it twice, so no, not a function. And that means it's the, that's why we call it the vertical line test. So the vertical line test tells you if something is a function. Okay? The horizontal line test tells you if that function is invertible. The horizontal line test tells you if you can find the inverse of a function, because not every function has an inverse. Some functions don't have inverses, some functions do have inverses, and the only way to know if a function has an inverse is to do the horizontal line test. So you'll notice this thing is a function, but does it pass the horizontal line test? It does not. And so technically we would say this function is not one-to-one. So let's define that real quick. Right here where it says one-to-one, underline it, and write passes the horizontal line test. A function is one-to-one if it passes the horizontal line test. If a function passes the vertical line test and the horizontal line test, that's a really nice function, and it's something that calculus wants to study. In calculus, we study really nicely well-behaved functions that pass both horizontal line tests and vertical line tests, and then we're like, game on, let's study those functions. But when they don't pass either the vertical line test or the horizontal line test, what we tend to do is just chop off part of the graph. So like, for instance, let's say that we had a graph of a circle, all right? Not a particularly good function. Does it pass the vertical line test? Fail. Boom. It does not pass the vertical line test. Hits it twice. Does it pass the horizontal line test? Fail. Hits it twice. So you know what we do in math? We take a function that doesn't pass the horizontal and vertical line test, and we just look at part of it, and we say, looking good. Let's study that part. Because that part passes the horizontal line test and the vertical line test. And then we just focus our attention on one part of the graph at a time. And now we say, this is a nice, well-defined function. All right? Okay. So then how, just by looking at the functions, do we figure out if something is one-to-one? We need to know if it passes the horizontal line test. And then furthermore, we want to find the inverse. So let's talk about those things one at a time. I think we have quite a few examples here to look at, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, we have a whole bunch to find out if they're one-to-one or not. So what would be the easiest way to find out if it's one-to-one? Yeah, just graph it. So everybody, I'm just going to rapid fire here, show you pictures of these graphs, and we can all make our own determination if it's one-to-one or not. And keep in mind, it has to be one-to-one in order to find the inverse. If it's not one-to-one, you cannot find the inverse. Okay. There we go. So the first one, 6x minus 2. Does it pass the horizontal line test? Yeah. So you could say 1-to-1. A nice way of writing 1-to-1 is not 1, 2, 1. That takes a lot of time. You can also write 1, 2, 1. It's 1-1. That's the short way of saying a 1-to-1 function. So you can say, yes, 1-to-1. How about the next one? X minus 2 over 3 plus 4. X minus 2, over 3 plus 4. Does it pass the horizontal line test? Yeah. Now notice, we're kind of making a fast and loose assumption here that I've zoomed out far enough, right? Like, couldn't it be that if I zoom out far enough, finally, whoops, it fails the horizontal line test? Right? I mean, we're looking at that right now. It just looks like a straight line. But what if eventually I zoom out far enough and it goes bloop, bloop, and then fails? Right? So when I just casually show us a graph and we're like, yeah, it passes the horizontal line test. Did we really prove it? Would you bet your life on it? You shouldn't bet your life on it. But like you zoom out enough and you're like, hey, I've zoomed out to like 5,000. I'm pretty sure. But again, you wouldn't want to bet your life on it. But for the context of this class, zooming up to 5,000, is a pretty good indicator that it is 1-to-1 and that it passes the horizontal line test. Okay, so let's try another one. Here we go. We've got square root 3x minus 1 plus 5. Did it pass the horizontal line test? Yeah.
The 5 isn't under the square root.
Oh, thank you. That pesky. There. Still passes either way, right? So there we go. That one does. It is 1-to-1. Let's try another one. The fifth root of 3x minus 1. Now, the fifth root of 3x minus 1, to type a fifth root, you actually raise it to the power of 1/5. Have we talked about that as a group? I'm not sure that we have. Folks, if you want to take a square root, that's actually x to the 1/2. If you want to take a cube root, that's actually x to the 1/3. And if you want to take a fifth root, that's actually x to the 1/5. And if you want to take any nth root, that's really x to the 1/n. So I'm guessing that you've probably seen that before, but just a nice little refresher. Now, take a look at this function. Does it pass the horizontal line test? Yeah. Does it pass the vertical line test? Now, see, again, this is why we can't really trust our eyes, right? Because right now, you might say, no, it doesn't pass the vertical line test. It looks like there's a vertical line that cuts through it multiple times. But again, see a graph, you really have to manipulate the scale to take a look and check. So I'm going to go, hold on, that's around 0.8 maybe. I'm going to go from 0.5 to 1. Well, it still looks like there's a vertical component there, but I'm thinking, no, there's not really a purely vertical component. Let's change that again from 0.3 to 0.34. See, now, again, this is challenging. As we zoom in more and more, we can see that it's curving away, and then it looks like it goes vertical. But then the question is, does it really go vertical? Now, looking at Desmos, you don't want to trust it because it looks like you have multiple coordinates with the same y value. But remember that those y values are just rounded to 4 decimal places, right? Can we really trust this graph to tell us whether or not it's vertical or if it's slightly curved? Probably not. I can zoom in a little more. I'm going to go from 0.3332 to 0.3334. And yeah, I'm thinking, no, it doesn't actually go vertical. From this point, it actually does start sloping to the right, ever so gently. Okay, kind of going on a tangent here. This thing, does it pass the horizontal line test? For sure. Yeah, it passes the horizontal line test, so it's 1-to-1. How about the next one down there? It's 3 minus the cube root of x minus 2. 3 minus the cube root. So that's x minus 2 to the 1/3. I gotta zoom way back out to find my function. I wish there was a way to reset that. 10, 10, 10, 10. All right. All right, does this thing pass the horizontal line test? Yeah. And how about this next one? 3x plus 4 squared minus 5. 3x plus 4 squared minus 5. Does that pass the horizontal line test?
But you're missing part of
I what?
You're missing part of it.
Oh, yeah, because it says strictly when x is less than or equal to -4. Now notice, see how they just did that? They just chopped off part of the graph. So I told you, if you have a graph that fails vertical or horizontal line test, they just chop off part of the graph and just look at the part that does pass both tests. So if we just look at that parabola, we'd say, no, it does not pass the horizontal line test. But they said, only look when x is less than -4. And so where's x is less than -4? They're saying only look to the left of the red line. Bloop. Now, does that function pass the horizontal line test? Yeah. Does that feel like kind of cheating?
Yeah.
Mathematicians just cheat. They're like, well, just look over there. Well, that's what they're doing. Because then what you could do is look at the part to the left, and then you could look at the part to the right and do the hokey pokey and shake it all about. Okay, so what was the only one that wasn't a function? Yeah, no, all of them were 1-to-1 functions, and therefore they are all invertible. Okay, so now that we have appreciated that, whoa. Oh no.
What have I done?
I'm just kidding.
Does anyone know what I have? Oh, there we go.
All right, so now how do we find an inverse? Everybody, we're going to follow the prescription for finding inverses. It has steps. We're going to write the steps down, and we're going to follow them. So, to find an inverse, okay, step one. Write f of x as y. So my original function is f of x equals 6x minus 2. That's my original. First step, I rewrite it as y equals 6x minus 2. Keeping in mind that y and f of x are synonymous. F of x is function notation, so it makes you think of input-output. Y is not function notation, but it makes you think of a coordinate, right? Because x, y, that's the coordinate right there. I plug in an x value, you get the y value. And that's why f of x represents the y value. Okay, step 2. Switch x and y. So I'm going to write x equals 6y minus 2. And right there, you might be like, whoa, 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 we just switched x and y. Don't think that's allowed. Right? Seems kind of arbitrary. Why did we just switch x and y? Well, because keep in mind, that's our definition of an inverse. We switch the role of input-output. So just like in a table, how I switched input and output, I switched those two columns. Right now, I switched the x and y because I'm reversing the role of input and output. That's what switching x and y means. It's not just some arbitrary thing like, hey, let's just switch the x and y, and later tomorrow, let's switch the t and the y. You know, we're specifically switching the order of input-output by switching the x and the y. Okay, step 3. And really, this solve for y. So now we're going to do some genuine algebra. We're not solving for an x-intercept, we're just solving for y. So how do we solve for y? It's really important that you feel good about this game called Tell the Story of y. Y is being multiplied by 6 and subtracted by 2. So what would I do first? Add the 2. So y is being multiplied by 6 and subtracted by 2, so I add the 2. That gives me x plus 2 equals 6y. And then continue solving for y. Y is being multiplied by 6, so we divide by 6. And so now what we have, and notice in my last step, I'm going to rewrite it so that y is on the left again, because we tend to have y on the left, f of x on the left. So I'm going to rewrite my final answer as y equals x plus 2 over 6. That is the inverse. This thing right here is the inverse of 6x minus 2. And the way we're going to show that is step 4. Just like the first step was write f of x as y, now we're going to write y as f inverse of x. Remember, f to the negative 1, we say f inverse. So f inverse is x plus 2 over 6. That's how you find an inverse. 4 steps. You start with the original function, you rewrite f of x as y, you switch x and y, you solve for y, and then you replace y with f inverse of x. All right, now you could be saying, Mr. G, I get it, I see the steps. How do I really know that f inverse is x plus 2 over 6 compared to the original function, 6x minus 2? What would I have to do to prove to you that these two functions really were inverses? You could graph both, or you could plug in numbers. Let's try plugging in numbers real quick, because I want you to believe it. So on the one hand, if I have the function 6x minus 2, I'm going to choose some pretty outlandish numbers to plug in for x, like 10 and maybe 30. All right, and then on the other hand, I'll do the inverse, which is x plus 2 over 6, and let's just see what happens. So if I plug in 10, 6 times 10 is 60, minus 2 is 58. And then if I plug in 30, 6 times 30 is 180, minus 2 is 178. So I just chose two totally random numbers into my normal function. This is my normal function, f. And my claim is that my f inverse should switch the order of input-output. So now if I come over here and I input 58 and I input 178, what should I get out? I better get out 10 and 30. If these are inverses, then I better get out 10 and 30. And sure enough, if I plug in 58, 58 plus 2 is 60, divided by 6 is 10. If I plug in 178, 178 plus 2 is 180, divided by 6 is 30. Now, did I really just prove to you that these are inverses? Well, that's not really quite a proof. I mean, maybe if I kept going, eventually I'd get to some really weird number like 173, which outputs to be like 4,806. And then I come over here and I do 4,806, and I run that through it, and I get 7. And I go, oh no, there's a problem. In which case you just disproved that they're inverses. But that's not going to happen because we follow the steps. If you follow the steps, it guarantees that you really do have an inverse. And this is just kind of anecdotal evidence to make you see that, yes, in fact, they are inverses. Questions, thoughts about inverses? Remember, ultimately, the bottom line definition of an inverse is that it swaps the role of input-output. That's the whole point of an inverse. It swaps the role of input-output. And all these steps that we're doing, we're going to practice now, it's just to create the function that will swap the role of input-output. So let's try another one. I'm going to go in order here. So step 1. Well, hold on. I don't write the original. I guess step 0 would be write the original. My original is f of x equals x minus 2 over 3 plus 1. Step 1, rewrite f of x as y. So y equals x minus 2 over 3. Step 2 was switch x and y. So now I'm going to write x equals y minus 2 over 3 plus 3. Sort of, sometimes I get so excited. So I wrote the original. I replaced f of x with y, I switched x and y, and now I just go about doing algebra. So this is just standard algebra, what we're about to do here. Y is being, so again, this is the story of y. What's happening to y? Y is being subtracted by 2, divided by 3, and added by 4. So the first thing we do is get rid of the 4. Because you always start at the end of the story of y. So I'm going to subtract 4 from both sides. So now I have x minus 4 equals y minus 2 over 3. And then you start the story of y all over again. This is algebra. I don't think you and I have spent much time talking about this, but this is how algebra works. You look at the variable you're trying to solve for, you tell the story according to PEMDAS. Y is being subtracted by 2, divided by 3, and whatever you say last, that's the thing you cancel. So y is being subtracted by 2 and divided by 3, I want to get rid of the divided by 3. So I multiply both sides by 3. Now watch carefully here. To multiply the left-hand side by 3, you better wrap that in parentheses, because you're going to have to distribute the 3. So now, and those 3's cancel. So now I have 3x minus 12 equals y minus 2. Finally, the story of y once again. Y is being subtracted by 2. So you can cancel out that subtracted by 2 by adding 2. So I add 2 both sides. And again here, my last step, I'm going to switch the y, put it back on the left. Y equals 3x minus 10. Now there was one more step, but don't just finish there. Because if you just write y equals 3x minus 10, it just looks like some function. We want to specifically notate that that's the inverse of the original. So since this was the original function, f of x, our last thing to do is write f inverse of x is 3x minus 10. Okay, there's one more thing that I want to tell you. How do we know? If you have two functions and they're genuinely inverses, then f of f inverse should equal x, and f inverse of f should also equal x. If you compose a function with itself, it should end up equaling x itself. If you compose an inverse with itself, if you compose an inverse with its own function, it should equal x. But it has to be both ways. It has to be f of f inverse as well as f inverse of x. This is actually the definition. A function and another function are inverses if either way you compose them, it ends up equaling x. So I want to show you one of them. In fact, I kind of want to show you both. So let's look at the first example, f of x. I'm going to do this one. So I'm going to write f really big. So my f function was 6 something minus 2. And then into that, I'm going to plug f inverse, which was x plus 2 over 6. So does that equal x? Question mark? If I plug f inverse into the original function, does it equal x? Well, my 6's cancel. That gives me x plus 2 minus 2. The 2's cancel. And yeah, it gives me x equals x. So that works so far. Now I'm going to try this one. I'll write the f inverse really big. That was something plus 2 over 6. And then into that, I plug in f of x, which is 6x minus 2. So now I simplify that. Does that equal x? Well, here the minus 2 and the plus 2 cancel out. That gives me 6x over 6. And the 6's cancel out, and I get x equals x. At this point, I have now proven to everyone on planet Earth that these functions are inverses. Right? Everybody now is going to agree. Because it's not just a matter of choosing a bunch of inputs and then showing that the roles reversed for input and output. But rather, this is the definition of an inverse function. Because remember, what do inverse operations do? Like plus, minus, multiply, divide, first square root. They cancel each other out. Which means that if you plug in a number, the whole thing ends up just equaling that same number. Okay, so that's the definition. I suppose we could do another one, but let's keep going. I want to get to some more complex possibilities. So let's look at 3, 4, 5, 6. Oh, we've got a bunch of those. Oh, and we're solving with radicals. Oh, is that the? That's not the end. What did I say? It is the end. Oh, does chapter 5 just have 5.1 and 5.2?
Yes.
Oh, we're getting drafts. Well, we're well on our schedule, so I'm not going to rush this. We're going to make sure we spend some quality time here. Let's find the inverse of number 3. I'll go ahead and use all my steps here. I've already got them written down. So recall, step 0, you just write it down. Well, I have to write it down anyway. Suppose you already have it on the paper. f of x equals 3x minus 1 plus 5. So what's step 1? Yeah, we write f of x is y. So I'm going to write y equals root 3x minus 1 plus 1. Okay. Step 2. Switch the x and the y. And that represents? Yeah, switching the role of input-output. By switching the x and the y, we are switching the role of input-output. Now I have x equals root 3y minus 1 plus 1. Okay, then step 3. We'll just go about doing algebra. Quite a bit of algebra. So for instance, let's look very carefully here at the story of y. What's the very first thing that happens to y? It gets multiplied by 3. That's the very first thing. Think about PEMDAS. Parentheses, exponents, multiplication, division, addition, subtraction. Y, first of all, is inside a square root, so that's kind of like a parentheses. So in here, what's happening to y first? The multiplication, not the subtraction. Because comes before in PEMDAS. Right, so y is being multiplied by 3, then what? Then subtracted by 1, then what? Not yet. Then square rooted, then added to 5. That's the technical story. And in fact, you can even go so far as writing the story. It's not the most compelling short story in the world, but you can write that story down to tell yourself and your audience what's happening. You could say, well, my story of y, still reach it. My story of y is, the first thing is that y gets multiplied by 3, and then it gets subtracted by 1, and then it gets square rooted, and then it gets added by 5. Now that might look crazy, what I just wrote down here on the board, but I hope that you can appreciate what I just wrote down. I just wrote down the story of y. What happens to y first? It gets multiplied by 3. Then it gets subtracted by 1, then it gets square rooted, then it gets added by 5. And what I just wrote down by writing down the story of y, it just gave me a list of things to do. So again, to solve now, y is multiplied by 3, subtracted by 1, square rooted, and added by 5. You always get rid of the last thing you said. So what are we going to do first? Subtract by 5. So I subtract by 5, and now I have x minus 5 equals the square root of 3y minus 1. And you'll notice I just took the last item off the list. But the story of y now remains the same. Y is being multiplied by 3, subtracted by 1, and square rooted. And again, I'm starting at the bottom of the list, working out. So what's the opposite of square rooting? Squaring. So I'm going to square both sides. That'll effectively cancel out that square root, and now I have x minus 5 squared, which I'm not going to FOIL out just yet. You could FOIL it out right now, but let's not get bogged down by details. Let's just finish the process. Let's finish this inversion process. So there, I just took care of the square root. So again, the story of y. Y is being multiplied by 3 and subtracting by 1. Again, we're working from the bottom up. So the opposite of subtracting by 1. So now we have x minus 5 squared plus 1 equals 3y. And I just took care of that step. And then finally, the story of y. Y is being multiplied by 3, so you divide by 3. There we go. Now, we're not done, of course. Now that we've solved for y, we need to, first of all, put y over on the left. Y equals x minus 5 squared plus 1 over 3. And the last step was write y as f inverse. So f inverse of x is equal to x minus 5 squared plus 1. And so apparently that's the inverse. Now, folks, I can't help myself. Sometimes I feel like I do PSAs for proper mathematics. Algebra, as an art, requires cancellation lines. I hope you all noticed that when I did algebra, I have a cancellation line here, a cancellation line here, another cancellation line here, and another one here. That's what algebra is supposed to look like. Algebra is the art of cancellation. So when you do algebra, there should be cancellation lines in every single step of the work that you do. That's algebra. That is the technology that was invented hundreds of years ago. It is the art of cancellation. So when you do your algebra, it should be fairly obvious and clear what all you just canceled out. Okay, well, folks, there. That's a nice instance of algebra. I know that you've all been doing algebra for years, but it never hurts to go back to basics and remind ourselves, what is algebra? Algebra is telling the story of the variable, doing that story backwards, canceling everything out with clear cancellation lines, and that's algebra. I see some people moving around. Is class almost over? Is that what's happening? I've turned my phone off during break because I had to reset it and I didn't turn it back on. So did I miss it? My phone didn't go off to tell me class was almost over. I have 1 more minute? 1 more minute. Okay, my phone's not even turning back on. Well then. So what shall we do, folks? Well, we're definitely not going to do another problem. I hope you like the whole story of X thing. I think that's very helpful. I hope you like the reminder to always do cancellation lines. You have all your steps. You can definitely now go home and do the homework for 5.1. I would recommend you do that. I would go home, immediately do section 5.1, email me with all your questions. Hey, what do you know? There's my arm. Oh, here. Class ends at 10:20? Are you sure it doesn't end at 10:30? I think something changed. After spring break, class goes till 11. Did you not get the update? The memo? Yeah, daylight savings. Our class goes till 11. All right, did everyone turn in your notes? Please come give me your notes if you didn't already. Hey there, Sarah. Is that for me? Wait, it is for me? It doesn't look like money.
Oh, no.
Oh, it's just forms for you to fill out. I understand. Here, you can throw that right back. Oh, you all have forms for me. How exciting. Now, I don't have that. Doesn't it have a pen? I can use.
I don't mind.
You don't have it.
Notes. Oh, yeah.
When are you going to bring it? Monday. That's a long time.
I don't have classes tomorrow.
Oh, I see. Well, then I guess that's what you're going to have to do. All right, now here, this is cyber. Now, this stuff isn't filled out here, so I don't know. Attendance issues, I don't think so. Have you ever been absent? Okay, but so I'd say no. Disruptive behavior, have you been very disruptive in the class? No, okay, well, that's good. I have to go check. See.
Okay, that's great.